good morning, everybody. Thanks for showing up. I think this is actually the biggest stage I ever got for a presentation. Much appreciated. So let me quickly introduce myself. My name is Jan Altenberg. I'm a trainer and project manager at Linutronix, which is a service provider for doing embedded Linux development. Well, you might have heard of us. So we do a lot of mainline development. For example, we've got the x86 maintainer at Linutronix. We do a lot of different mainline development. And actually, one thing we do is, on behalf of Linux Foundation, we're trying to get the real-time capabilities of Linux into mainline. And that's basically the topic of my talk today. I would like to give you a brief introduction on using real-time systems with Linux, or how to make Linux real-time. So this is not going to be a very technical talk. This is basically an overview of what you could do, what's possible, what not, and giving you some historical details about real-time in Linux. So I will talk about basically about the definition of real-time. So first of all, before we start to look into Linux and real-time, we need to get an idea basically what's the definition of real-time and who needs real-time systems. This is how we're going to start it today. Well, then we will look into Linux in real-time. You will see we have several approaches on making Linux real-time. We have several different approaches, like we have real-time systems with Linux around for more than 15 years right now. So we have a lot of different historical approaches on how to make Linux real-time. So I will show you the most important ones and the ones which are still, well, developed today and which are used in the industry. We will also look into the results and the latencies you could basically achieve with a real-time Linux on a specific platform. So basically, we will look into a Cortex A9 dual-core system and see which latencies could be achieved with different real-time Linux approaches. So this is basically what I'm going to talk today about. So now, let's get started. Now let's quickly rethink what real-time is about. And for me, this definition is pretty important because still, when we do presentations or trainings on this, we can see that there's still a lot of confusion about the definition of real-time. So basically, one definition we get really often is, well, real-time is just about fast responsiveness. It's fast execution. Well, I don't know, is anyone in here who would agree with that? No one? Yeah, you're experts already. So basically, yeah, this is not the definition of real-time, right? But you get this definition very often. Real-time is about fast execution. It is not. Well, another definition we get quite often is, well, it's about performance, which is also not true, right? But, well, we have to admit that the word real-time might be a bit confusing. Also, it's not fast execution, it's not performance. But, well, if we would go outside the hotel and ask people on the road what's real time, they would tell us, well, maybe it's the real time, just the time of the day. Basically, well, we have a clock real time in Linux, right? But that's the time of the day. But this is also not what we are going to talk about today. So real time is kind of confusing, so this is why it's that important to get a clear definition of what we're going to talk about today and to get it in the correct context with Linux. So it's not about fast responsiveness, it's not about performance. Basically, it's all about determinism. So when we talk about real time, we talk about timing guarantees. So you need to execute something in a specific time frame, and you need a guarantee for that. So basically, the definition would not be as fast as possible, it would be as fast as specified. And this is the thing which is important about real-time. So, well, if 30 seconds is enough for you, well, it's okay. It's your definition of real-time, but you need a guarantee to meet this. So this is really important to get this point. When we talk about real-time, it's all about determinism. So when I talk about Linux and real-time today, I'm going to talk about deterministic timing behavior with Linux. This is basically the idea of this talk. So, well,
Not to be personal, but could you maybe get your about
Ah. Okay. Could you help me out here? Maybe we could wait a second.
It's not about your fashion choice, right?
Well. Okay. Yeah, let's try that again. Just let me know if it's making trouble again. Well, yeah, sorry for that. Okay, thanks for telling me. So once again, we've been talking about determinism. So now, when we start about talking about real-time Linux, the next question would be, who needs real-time Linux? So basically, when we talk about real-time, we have to think that the correctness of your algorithm you're trying to calculate is not just based on the correctness of your algorithm, it's also based on the correct execution time. Which means if you don't do the calculation within the correct time frame, this will lead to an error condition. So this error condition in a real world example might be the product you're trying to manufacture is broken, your machine will break or something. So missing the time slot will lead to some error condition. And actually the worst case situation would be if you miss the time frame, actually someone would get hurt, right? So if you get into that situation that the machine gets broken or your product or someone gets hurt, this is basically the moment where you need to think about real-time requirements. So now one last point on the definition of real-time. And this is something we hear really often when it comes to Linux and real-time. We get some word like soft real-time. So I don't want to get really deep into that topic, but please forget about this word. So we don't talk about soft real-time. Let me give an example, like if your wife would tell you she's kind of pregnant, would you believe that? No, you wouldn't, right? So, well, she can be pregnant or not. So same for real-time. Let me give you another example, like if you think about the use case and missing the time slot will lead to an error condition. So basically, I'm interested in not getting hurt. Well, not getting hurt for most of the times wouldn't be acceptable for me. So basically, that's the same for real-time. So you can be deterministic or not, but there's nothing in between, right? So please forget about this soft real-time word. It's just crap, right? So we can be real-time or not. So when I'm talking about real-time today, we talk about hard real-time and deterministic timing behavior. That's it. So, well, when you get into a new technology, the first thing you do is you're trying to check out who else is using this at this very moment. So basically, you don't want to be the first one, right? So, well, for real-time Linux, we have many users around in this world which are currently already using real-time Linux systems. So we have a lot of industrial applications. We have the automation industry. Actually, already automotive industry. We've got multimedia systems. We even got, well, aerospace systems in non-safety critical applications. And we have financial services, which is pretty strange, but they run it on big server machines, for example, for high-speed trading and stuff. So they need a real-time operating systems, and these guys are actually using real-time Linux. So we already have a lot of users of this system around. So when it comes to real-time and the real-time operating system, we need to check a couple of requirements for this. So we need deterministic timing behavior. And to get deterministic timing behavior, one of the most important features an operating system needs is preemption. Well, basically, you need to be preemptible at most of the parts in the operating system because a high priority task needs always to be able to preempt a low priority task, right? So this is the most important requirement for a real-time operating system. And, well, you also have a couple of special situations you need to deal with. One of these is the so-called priority inversion. So some of you might have attended the Realtime Summit yesterday. They had a couple of discussions on this. So in real-time systems, we have this classic error scenario. So basically what could happen is, just think about static priorities. We've got 3 tasks. Task 1 is the highest priority task. Task 3 is the lowest priority one. So basically now these 2 tasks need to share a resource, so we need some kind of synchronization. So what would happen right here is task 1 is blocking because task 3 is holding that resource, which is basically not a problem at all. But now what could happen is task 3 gets interrupted by something in between before it can release the lock. So the result would be a high priority task is waiting for a low priority task, and the lock never gets released until task 2 stops running. So this is a classical error situation in real-time systems, and actually a real-time system needs to deal with that. So we have a couple of strategies, and actually Linux can already deal with this situation, and you don't even need a real-time extension. What Linux does is, in this situation, we've got the so-called priority inheritance, which is basically, to keep it pretty simple, in this situation what we would do is we would boost task 3 to the priority of task 1 until the point it releases the lock, so we can avoid task 3 to get interrupted by someone. So it's not just a preemption, we have to deal with a lot of different use cases which are very specific to real-time applications, and we need to think how we can get these features in a general purpose operating system like Linux. So traditionally, we have 2 approaches to make Linux real-time capable. And well, the oldest approaches are the so-called dual-kernel approaches, which are basically not doing real-time in Linux. It's like having real-time in Linux on the same system. So these guys just introduce a microkernel which is doing the real-time. And well, the other idea is just to find a way to make Linux itself real-time capable. So let me try to explain that. So this is the classical dual-kernel or microkernel approach. So what these people do is they do a simple real-time kernel. So this part is just, well, doing the real-time stuff. And the idea is that Linux is just running on top of this microkernel as a low priority real-time task. So if you don't have any critical real-time applications running, well, Linux can get some runtime. So this is the basic idea of these microkernel approaches, which looks quite clever at the first glance. But well, if you think a bit more about this approach, you've got 2 problems you have to solve, right? Because someone needs to maintain that microkernel, right? And needs to port it to new hardware. So just think about the amount of ARM SoCs which are coming up right now. So this is exploding. So someone needs to maintain a microkernel, needs to port it to new hardware. This is a huge effort. And well, basically these communities are not as big as the community of the Linux kernel. So this is basically something you have to deal with in this situation. Well, and we've got another point right here. Well, you can see Linux is not running on the physical hardware, right? So you need some kind of hardware abstraction layer inside Linux just to make it capable to run on the microkernel. So basically you have 2 things to maintain. You need to maintain a microkernel, and you need to maintain a hardware abstraction layer to adjust it to the most recent Linux versions. So also this is a big effort, and basically this is one reason why most of these approaches are usually a step behind of the Linux development, because they just can't keep up with the fast Linux development. But well, these were the first approaches we had for real-time in Linux, and these approaches are still around. I'm going to give you 2 examples on these implementations. So the other idea would be, instead of moving the work to the microkernel, finding a way to make Linux itself real-time capable, which basically looks like a huge task. Well, basically that means you would have to touch every single file in the kernel. And I can tell you we had to. But basically, you can manage that. So at the first glance, looks like a big job, but at the end of the day, the result you have right here is, well, it's just you have the real-time in Linux. So you have no microkernel to maintain. You have no hardware abstraction layer to maintain. And you can just use the standard tools. You can just work with Linux. So basically, if you would have the choice to make Linux real-time capable, that would be the way you would want to go. So, well, let's have a look into some real implementations of real-time Linux. So, one of the very first approaches we had for Linux and real-time was RTAI, the so-called real-time application interface. This comes from Italy, from the University of Milano. Actually, I think they used it for a couple of aerospace applications. And this was actually the first real-time Linux I was using, right, 15 years ago or something. So this approach is around for years. So RTAI is a classical dual-kernel approach. So basically, this kind of implementation. So RTAI had a couple of drawbacks when using it. So basically, when you write, so this is actually still around and maintained, right? But the basic idea when using RTAI is you write a kernel module. You write a kernel module which is basically scheduled by this microkernel. But basically, it's like kernel development. So it's not like writing an application. So it's really hard to deal with, hard to debug, hard to get into it. And basically, one thing I had to do this for an industrial customer. Well, since most of the parts are kernel-based, it's GPL code, which is not a big deal if you do open source software. But, well, for an industrial customer, you usually also have some closed source parts, so you always had to think about which parts you can put in userland without real-time and which parts you can put into the kernel with real-time approaches. So basically, doing real-time with RTAI was pretty hard because most of the stuff is done in kernel space. They had some interface for doing real-time in parallel to user-space tasks. This was called LXRT. Well, I tried it several times, so for me it was not working pretty well. So I got told it got more stable these days. I have to admit I haven't tried it for a long time, but for me it never worked pretty well. So basically, usually for RTAI you have to stick with the kernel space. Another problem we had with RTAI was one of the design goals is basically not portability. It's more or less for a given number of hardwares to achieve the lowest latencies you could possibly get. This was basically one of the RTAI design goals. So this means that the number of supported platforms, it's quite limited. Yeah, it's basically x86, 32-bit, 64-bit, a couple of ARM platforms, and that's it. So if we look into the RTAI design, it basically looks like this. And this is the classical dual kernel approach. And basically, you can identify the two problems I mentioned about microkernels. You've got to maintain this real-time kernel, and actually you can see this real-time kernel is just handling everything which is related to the timing critical things in the system. So you have to maintain this real-time kernel, and right here, you have to maintain this hardware abstraction layer. So these are the two problems I told you about. So this is a classical example. And Linux is just completely in a different world. The only thing you've got is a simple communication mechanism to synchronize both worlds. But that's basically the idea. And you can nicely see in this figure that basically it's not real-time in Linux, it's just real-time in Linux in parallel on the same system. That's basically what you do with these approaches. Well, there's another approach which is called Xenomai. And this is still pretty popular. So this is still used in a lot of industrial systems. It's still around on the market. It's also quite old. So I think it was founded in 2001, so it's around about 15 years, or in 2000, like it's more than 15 years now. Well, the reason why it's still that popular is that these guys had one advantage. They always had a proper solution to have real-time in user space. So you didn't have to do everything in the kernel. So userland is much easier to deal with. So this is basically one thing these guys made pretty good, and they had a nice idea for real-time in user space. They implemented the so-called skins, which is basically a emulation layer for the API of different real-time operating systems. So you have, for example, a PSOS skin. You even have a POSIX skin. So if you have a pre-existing code base for some operating system, you can reuse it with the Xenomai, which is pretty nice. So basically, these layers are not feature complete. It's a subset usually. Even the POSIX layer is just a subset of POSIX. But, well, you can actually reuse a pre-existing code base for rapid prototyping, porting your application very fast to Xenomai. So that was basically a nice idea. They have a lot of supported platforms, way more than RTAI does. Maybe also reason why it's more widely used in the field than RTAI. But it's still a dual kernel approach. So also these guys are using a microkernel for doing the real time. So basically, we suffer the same problems. We've got the microkernel to maintain. We've got a hardware abstraction layer to maintain. And, well, even if you can have real-time in user space, there's one additional problem. You can't use the standard C library. You need special tools and special libraries to deal with Xenomai. So even for POSIX, you need to link your application against the Xenomai POSIX skin. So it's not standard glibc. You always need special tools and special libraries to deal with these microkernel approaches. So the handling is way more complicated. So if we look into the structure of Xenomai, basically looks like this. It's actually not that different from RTAI. You can see it's a classical dual kernel approach. We've got that microkernel, which is dealing with the hardware right here. You've got the real-time tasks running on top of that microkernel. But you can see a small difference. You can see that part, which is called nucleus. And you can see that code path, right? So we get real-time into user space, which is much easier to handle than the kernel part. So this is a big advantage, but to use this, once again, you can't use any standard tools of Linux. You need to use special libraries and stuff. So it's much easier, but still some special tools are involved. So let me summarize the dual kernel topic for you. Well, the dual kernel topics, the dual kernel approaches have been the first ones we had around on Linux for a couple of reasons. Because when these approaches have been invented, we didn't have preemption and stuff in the kernel. So implementing real-time was pretty hard. So basically, this was the obvious approach. These approaches are still around on the market, but we have a couple of drawbacks. So we've got a special API, special libraries you have to link against. So this is basically one drawback we have. Well, special tools and libraries. We need to maintain a microkernel and the hardware abstraction layer. So basically, you're usually a step behind of the Linux development. So this is also a big issue with these approaches. And last but not least, just remember, we also have high-end users like financial services and stuff for real-time Linux. So these guys are not running real-time on a 2 or 4 core machine ARM. These guys are running on a S390 with I don't know how many CPUs. So for these guys, we have, with these microkernel approaches, we have a bad scaling problem, because basically these microkernels are known to scale pretty bad on big systems. So they usually scale up to 8 or 16 CPUs, but if you get more CPUs, they actually don't scale pretty well. So we have one approach to make Linux real-time, but basically these approaches have a couple of issues. So for that reason, people started to rethink if there just wouldn't be a way to make Linux itself real-time capable. And well, actually, we have now one approach, which is called Preempt RT, or the so-called real-time preemption patch. So the reason for this name is what we basically do is we just introduce a new preemption model to Linux, which is called real-time or full preemption. So this is why it's called a real-time preemption patch. This is a classical single kernel or in-kernel approach making Linux itself real-time capable. And well, basically this approach is now around for 12 years, so it's also quite old. It's widely used in the field. It was basically founded by Thomas Gleixner and Ingo Molnar. These two guys in 2004 started a lot of real-time Linux development. They started to coordinate their work, and the result was the real-time preemption patch. Well, we have a huge community for this development right now. So basically the reason for this huge community is that actually most of the parts of this development are right now already included in the Linux kernel. So 80% of their development already made it into Linux. So that's the reason why they have a huge community. So basically, if you're using Linux nowadays and look into the timers, the interrupt handling, tracing infrastructure, priority inheritance and all that stuff, all these features were basically originally developed for the real-time preemption patch and were pushed back into mainline. So this is the reason why we have so many users for this approach. Basically, since this approach makes Linux real-time itself, you don't need anything special to know about it. It's just if you write a real-time application, you just do a simple POSIX application, which means you can buy a 30-year-old book, like about POSIX real-time programming, and basically you know how to write a real-time application for preempt RT. You don't need any special libraries or stuff. You just use your standard C library. So this is the big advantage of making Linux itself real-time capable. So we also have a high acceptance in the community for the real-time preemption patch. So what's the reason for this? So basically, as I told you, we have a lot of features which came from the real-time development into the mainline development. So basically what we did, we added some powerful features which are not just useful for the real-time users, which are useful for everyone. So basically, these guys made Linux a better operating system also for all the other users. So this fact got them a lot of acceptance in the community. And the other reason is that, well, when they made Linux real-time, everything got preemptible. So we found a lot of race conditions and locking problems, fixed these and pushed them back into mainline. So actually, we improved the stability of Linux a lot. And this is also one reason why these guys have a high acceptance in the community. So they're not just focused on their work, they just get some more quality into Linux. So basically, the mainline integration of real-time started a long time ago. And actually, I just checked this these days. The mainline integration started in 2006. So this is now actually 10 years ago. We started to push the first features into mainline. So this is an original statement from Linus Torvalds from Kernel Summit in 2006. So the reason for this statement was, usually if you want to get a new feature into Linux, he wants to know a use case for this. So who the heck is using real-time on Linux? So actually, one developer was telling him, well, I've got a customer who's running welding lasers with Linux already with a real-time extension. So, well, that was the answer of Linus, like, well, doing a welding laser with Linux is kind of crazy, but, well, we are all kind of crazy, so I'm fine with you doing the real-time stuff. So, sounds funny, but basically that was the starting point of the mainline integration of the real-time Linux development around about 10 years ago. Nowadays, you still need a patch to have the real-time stuff. It's like 20% of the original size. We got most of the stuff in the mainline kernel right now. You can get this patch for every second kernel version. And currently, the Linux Foundation is pushing the mainline integration. So the main goal is like having the real-time capabilities within Linux within the next 2 years. So this is basically, we're doing that development on behalf of Linux Foundation. So this is basically the idea. So how did these guys manage to make Linux real-time? So we need to remember again, what's the main requirement for real-time operating system? And the main requirement for real-time operating system was preemption. To achieve deterministic timing behavior, we need preemption. So these guys had to find a way to maximize the preemptible sections inside the Linux kernel. So basically, well, this is a very simple explanation, but this is basically what they did. First of all, they had to rework the locking primitives to, well, minimize the atomic sections inside the Linux kernel and to maximize the preemptible sections inside the Linux kernel. So basically what they did was reworking the spin locks and finding another method to deal with these situations. One idea, but yeah, just basically reworking the locking infrastructure. Basically, at some point, the real-time preemption patch was also called the sleeping spin locks patch. That was the reason, because we had to rework all the locking primitives. Well, and they had another pretty cool idea. Another section in the kernel where you are not preemptible is basically the interrupt context. So what these guys did was, instead of running the interrupt handlers in hard interrupt context, they moved it to a kernel thread. So what you basically do is when an interrupt arrives, you don't run the interrupt handler code, you just wake up the corresponding kernel thread, and the kernel thread will run your interrupt handler. Which has two advantages. Basically, the kernel thread is interruptible, main advantage. And, well, it shows up in the process list with a PID, so you can even put a priority on your interrupt which is arriving. So, well, you can give a low priority on your non-important interrupts and give a higher priority on your important userland task. So running it into a kernel thread was actually pretty nice and pretty cool idea. And actually, this is also one of the features, the threaded interrupt handlers, which are already available in Linux mainline. So even in mainline Linux nowadays, you can decide if an interrupt handler can run in hard interrupt context or in threaded context. So actually also one of the features which came from preempt RT. So, well, this is just last but not least a quick overview how the real-time preemption patch, this single kernel approach, is working. So basically, well, you can't see any difference to standard Linux. It's just standard Linux, right? Just with a new preemption model. So there's nothing special about it. So if you do a kernel driver, it's just a Linux driver. If you do a real-time application, it's just a Linux application. So you don't need any special libraries or special API. You just do a Linux driver or POSIX application. That's it. So now I promised that I will show you some results in a real-world example, which latencies you could possibly achieve with these real-time Linux extensions. So what we did was we took a simple ARM board with a Altera Cyclone 5. Actually, we took the Rocket board, which is a community evaluation kit of that SoC, and we did a couple of latency measurements. And what we did was we did the same measurements for Xenomai, like a dual kernel approach, and for preempt RT, a single kernel approach. So, well, there was actually a special reason why I wanted to do these measurements. Because, well, if you Google for these topics, you will find a lot of papers comparing Xenomai, preempt RT, and RTAI. And basically, most of these papers claim that the dual kernels are way faster when it comes to latencies. So, and actually, for most of these papers, well, I was able to figure out that, yeah, the preempt RT systems are most of the times pretty misconfigured. So, my idea was to get a fair comparison of dual kernel and single kernel approaches and see which latencies could be achieved. So we actually took one Xenomai expert and one preempt RT expert, gave them the same board, gave them a task, and then just tried to compare the results. That's basically what we did. So I think that was pretty fair, right? So, but yeah, let's wait for the results. So what we did was we did IRQ tests. So we fired IRQs with a frequency of 10 kilohertz. We took the OS-ADL latency box to do that. I will tell you how this box is working later on. And we put the system in a worst-case scenario. So basically, since you want to guarantee timing behavior, you need to guarantee this, yeah, well, even in a worst-case situation, which is usually high CPU load, high memory load. and a lot of work for the scheduler. Well, we achieved that with a tool which is called Hackbench. So this is basically how this tool works. You've got process groups with 20 clients and 20 servers, and the idea is that each client sends 100 messages via a socket to each server. So you've got a lot of inter-process communication, and you can tell Hackbench how many groups to run. So for example, if you take 40 groups, it's 40 times 40 processes, so you have 1,600 processes doing weird inter-process communication. So basically, this is a real worst-case situation because, yeah, the scheduler continuously needs to take decisions. You have high CPU load, you have high memory consumption. So this is basically the real worst-case situation for your system. And while doing this, while running this, we just started to fire interrupts and measure the latency. So this is basically what we measured. Like, once again, I'm taking myself as an example. Like, we get an external event. Like this morning, the alarm clock was ringing. I need to react to that and get out of the bed. Basically, this is what we did on the embedded board. We just fired an external event and did a simple driver who needs to do this reaction. And what you can do with the latency box is this latency box can record all the samples you get and do a nice histogram for you. Because this is also quite interesting, just not to get the worst case latency, also the variety of latencies you could get. Well, basically, once again, taking me as an example, today it was quite easy, but well, I might go drinking tonight, so tomorrow it might be quite hard to get out of bed, so it's not always the same latency, so you have some variance in it, right? So this is the so-called jitter, and that's why we want to record all the samples and put them into a nice graphic. And this is basically what the OSADL latency box can do for you. So this box can fire interrupts in a pre-configured frequency. So in our case, there was 10 kilohertz. So it has an output pin, triggering a signal. You send this signal to your test system. Your test system needs to trigger a pin, which is connected to an input pin on the latency box. And the latency box will just measure the time in between and record all the samples. So we did this for 12 hours, which is not very long, but it's the bare minimum to get a good idea of the real-time behavior of a system. So this is really the bare minimum you could take. It's not really long, but it can give you a good idea. So this is basically the measurement we did. Firing interrupts with 10 kilohertz, getting a reaction from the target system, and measure the reaction time. Every measurement has been taken with the latency box. So actually what we did was we had two use cases, and the most important one was the reaction time of a user space task. And this is basically the real-world example. If you need to react to an external event, basically you need to synchronize your user space task with some interrupter stuff, like some field bus, interrupt, or whatever. But basically, you want to do your work, your homework, your real calculations in user space. So this is basically the most important example. So that was the reason why we took this as the first measurement, measuring the latency from the external event arriving into your application and triggering the GPIO, which goes to the latency box again. So well, we started these measurements on Xenomai. These are basically the results. So as you can see, we did a nice histogram. Well, you can see the latencies on this axis. You can see the number of samples right here. So now the average was like 30 microseconds reaction time. But basically, the average is not the number we are actually interested in, right? So we want timing guarantees. So if we want to look into timing guarantees, we need to check for the worst case. Well, you can see the worst case latency right here, this small peak. So we had actually one sample which was around about 90, 95 microseconds. That was the worst case latency we got on that device with a 10 kilohertz interrupt. So let's say 95 microseconds worst case latency, which is actually not too bad for a user space application. So now we did the same measurements on preempt RT. You can see, well, the variety, so the jitter is a bit bigger, yeah, right here. But you can actually see this is the worst case latency we got, which is pretty much the same we had for the dual kernel. Like it's even slightly better, but I would say it's pretty much the same. A bit less than 100 microseconds what we could achieve. So, well, basically this can prove that we don't have that big difference you can find in a lot of measurements which are around in the internet between dual kernel and single kernel approaches. So in this test case, we had pretty much the same latencies on the dual kernel and single kernel approach. And well, actually one thing we tried right here is, well, since PreemptRT is a standard Linux system, so we can actually use all the standard Linux features. So we were wondering what would happen if we just isolate one CPU that was a dual core system. What would happen if we start isolating CPUs for just handling that interrupt and see what happens? So basically that was the next measurement we've taken, doing the same measurement with an isolated CPU. So you can see it gets slightly better, like from 90 to 80 microseconds. But this is basically, well, you don't hit a specific worst case because it's running on a different CPU. Well, this is done pretty often in real-time systems that you just isolate a specific core for some specific tasks. So, well, since there was a standard Linux use case, it was quite easy to isolate this core. So we've got this comparison. I think the most important graphs are these two right here, the green one and the red one. The red one is just a PreemptRT without any special configuration, and the green one is Xenomai without any special optimizations. You can see basically the latency we got for the user space task was pretty much the same, which is actually pretty cool when we compare a dual kernel and a single kernel approach. So we did another measurement, and well, actually I was not really happy with that measurement. Well, you might get that if you look into that slide, right? What we also did was we measured the kernel latency. And what was the reason why I was not happy with that measurement? Because basically, in my opinion, what you basically do, you compare a full-featured Linux system with the reaction time of a microkernel. Well, you can discuss about that, but in my opinion, it's not a fair measurement because, yeah, we compare Linux and the microkernel. So basically, in my opinion, we compared apples with pears. But basically, the results were actually quite interesting. So I would like to show the results right now because this is the result for Xenomai. And well, if you look in the internet, when we got a couple of measurements in the internet where just dual kernel approaches were 300 or 400% faster than a single kernel approach. And basically, yeah, I was expecting something similar right here. So we got 30 microseconds for Xenomai. Well, and if we check out what we achieved with PreemptRT without any optimization was like, well, it's slightly better than the user case-based latency, but well, we need to remember we just go into a kernel thread right here. So the difference is not that big. But now if we start to optimize this use case and just once again start isolating the core, we even get down to 60 microseconds latency for the PreemptRT, which is basically, if you compare a microkernel and, well, a full-featured Linux system, I think this comparison is not too bad. 60 microseconds is actually pretty fast on that kind of CPU. So the difference is not that big as you would expect, and not that big as a couple of measurements in the internet claim to. So actually, we're getting pretty close with the single kernel approaches. So now we did one last measurement on the kernel latencies. Well, and basically the idea was we were running on an ARM platform, and well, I was saying, well, we compare apples with pears, but well, if you go with the microkernel, you might be willing to accept a couple of limitations on your system. So I was thinking about, could we also put some limitations on the PreemptRT system and see if that could somehow improve the latencies? And well, the idea I had was just I was just curious how that would improve the timing behavior, just trying to use the FIQ feature of the ARM CPUs, which is a hardware feature. It's a special interrupt vector on ARM, which is running in its own context. So it's very limited in the things you could possibly do. It's living in its own world, so it's very limited what you can do. But well, when I'm willing to accept limitations, basically this might be an option. So what we figured out was, well, we've got 10 microseconds or even less average latency, and you can see the worst case is also around about 30 microseconds. And that was actually a pretty interesting number, because if you compare this, it's also 30 microseconds. So we are quite sure we just hit a hardware latency in this measurement. But we didn't have the time to track this down right now, but we've seen this on similar architectures. With Cortex A9 CPUs, we see the similar latencies. So really looks like a hardware thing. So well, this is the final comparison of the kernel side. So taking into account that we compare a full-featured operating system with a microkernel, actually these numbers are not too bad. And well, we need to remember, and that's the conclusion, with the preempt RT patch, we have a single kernel approach, which is basically nowadays the de facto standard for Linux, and it's getting integrated in the mainline Linux development. It's pretty simple to use. You can use standard C library, nothing special. It's available for every second kernel version, so it's the standard, it's easy to use, and it's basically for the most of the use cases, the microkernels don't have better latencies, so basically the latencies you can get are really comparable. So basically, if I should give you a recommendation, you know, preempt RT would be the way, because it's the standard and the latencies are pretty good you could possibly get. And last but not least, well, if you're willing to take limitations instead of going with the microkernel solution, you could also check out which features your hardware is offering, like the FIQs on ARM. You can use that. We've got support for that in Linux, but you need to be aware of that the things you can do with these hardware features are actually pretty limited. So well, that was basically all I wanted to tell about real-time Linux. So it was pretty high level, I know, but hopefully it was quite useful for you to get an overview about real-time Linux. So, well, basically, thanks for listening, and well, feel free to ask any questions. Any questions? We've got 1 minute left. Is there a mic? No?
When you did the comparison by isolating the CPU on preempt RT, what did you do with Hackbench? Did it only run on the, so did you effectively take Hackbench and limit it to one CPU and then your
Yeah, it was, yeah.
So it was half the load at that point?
Yeah, that's true, yeah. Basically, yeah, what we basically did was pretty simple. Just we booted with isolate CPU, so we just got the housekeeping stuff on the real-time CPU, and all the rest was just running on the second CPU. So basically, it's half the load, right? Yeah, that's true. Any other questions?
For my case, the engineering approach is somehow missing, because as I said in the very beginning, if you're talking about hardware systems, then task needs to be finished at a certain point in time. And you have to commit to time guarantee. But as you showed, you're measuring, and then you're measuring for 12 hours, and then there's one peak which is worst case. But what if in 24 hours there is another peak at 100, and then you're dead? So
Yeah.
what me strikes like for years is there should be some infrastructure, because actually when I was at university, you can calculate schedulability of tasks, how to arrange them.
Yeah.
There are models and engineering models, not just trial and error. Because actually, if you change something about the system, then you always have to do the measurement again. And if you, it's like the search for the black swan.
Yeah.
You can never be sure that you're not will not be killed.
Well, it somehow is. But I agree with your point. This is basically a problem we have nowadays. So basically, I think your point is this: with these measurements, we don't have the mathematical proof of that we can't miss things. But the main reason why we don't have this nowadays is basically for modern system like that board we've been running on, we don't have the option to do the mathematical proof. Nowadays it's not possible anymore. Like in the good old days of microcontrollers, you had a fixed frequency, you didn't have any caches, so you just had to calculate the numbers of instructions of the code path, calculate which code path you go, and it was quite easy to calculate the latencies you get. Basically, the problem you have nowadays, we've got even hardware features which are not reliable. So basically, we don't really have the option to do a mathematical proof, but you're right. So with a 12-hour measurement, basically, I can't be sure that I have a timing guarantee. So what we basically do is to hit this point, to address this point. Since we don't have the way of a mathematical proof, we try to run long-term tests, and not just 12 hours. So like you might have heard about the OSADL. They run a test farm which is doing like long-term tests about 1 year, 2 years, 3 years, and you can actually get all the timing samples for a long time on these boards. This is basically one point we try to address this, but in my opinion, we don't have the option nowadays to do the mathematical proof.
But those kinds you could never use in medicine. So if you cannot mathematically prove, you cannot use in medicine.
Well, yeah. So I agree. Well, the use cases might be limited, but well, we still have a lot of use cases where you might need just a small RTOS system which can be mathematically proved. So I agree on that. But basically, for the huge SoCs and a complex system like Linux, there's no way to do a mathematical proof.
But actually, when you're talking about simulation, so for instance, when I get it wiring, so it simulates, really emulates the whole CPU, and it can also cache prediction everything. So if you use such kind of instrumentation machine underlying, so wouldn't that be a feasible approach to get all those values you need, so you can mathematically instrument the whole code?
Well, yeah, actually I never thought about that approach, but I think that the main problem is not just the code. And once again, the main problem we would suffer nowadays, in my opinion, is the hardware which is behind. You just need to think about, we've got up to 3 or 4 different caching levels nowadays. And actually we've got CPUs nowadays which are reordering instructions for us. So basically, even if you have the proof for the code, you still have the problem that you don't have the proof for the hardware. And for Linux, actually, we don't know on which hardware the Linux system will run at the end of the day. So that's basically the problem, in my opinion, here.
You're heading for the measurement process.
Yeah. But well, actually, if you're interested, we could continue the discussion in the break.
Yeah, I'm not satisfied because actually, if you want to do it strictly, I couldn't control a nuclear power plant.
Well, yeah, you've got a couple of other issues there, like safety requirements and stuff. But yeah, I agree. But well, I think we're running out of time right here. But if you're interested, we could continue that discussion in the break. So, well, yeah, I think time is over. So once again, thanks for listening.